Hi, today we will be going over Chapter 11.3, the integral test and estimates of sums. The integral test is used to find whether a series is convergent or divergent without finding its explicit sum. Now there are three requirements for the integral test. The integral test must be used on a series that is positive, decreasing, and continuous. Now, the series only has to be ultimately positive and ultimately decreasing as n approaches infinity. If f of x integral converges, then the summation of a of n converges. If the integral of f of x diverges, then the series a of n diverges. Now the proof for this is, let's say this is the graph of f of x and this is the graph of a of n starting from 2, so going left. Now this is an underestimate. If f of x converges, then that pushes a of n to converge. But for this one, this is f of x and this is a of n, where a of n starts from 1 and goes right. Now, this is an overestimate. So if f of x diverges, that means that a of n is pushed, so it diverges also. Now let's do a practice problem for the integral test. This problem asks, find the values of p for which the series is convergent. Now we want to use the integral test for this. So first we have to check if it's continuous, positive, and decreasing. And it is all of that for this series. Now, solving this integral, we get for p is a number. And this equals to Now, for this to be convergent, the integral must converge to a number. Now, this number can only converge if p plus 1 is less than 0. Otherwise, if p plus 1 is greater than 0, the top number would go to infinity, and that would make it divergent. So that means that p must be less than -1. Next is the p-series. Now the p-series takes the format of summation of 1 over n to the p, where p is a number. The p-series states that when p is less than or equal to 1, then the series diverges. If p is greater than 1, the series converges. Now let's do a practice problem. This is 11.3, number 41, and it asks, for what value of b is this series convergent? Now, we want to use p-series, so b of ln of n can also be written as e to the ln of b to the ln of n. Now, because this is a multiplication, since exponents are multiplied, this can also be written as e to the ln of n to the ln of b. Now we can cancel out these two, e to the ln, and just write n to the ln of b. But we want to get this into the format of p-series, so we write 1 over n to the -ln of b. For a p-series to be convergent, p needs to be greater than 1. So -ln of b needs to be greater than 1. Solving this, we get b is less than 1 over e. Next is estimating sum of a series. Next is estimating sum of a series. To find how accurate an approximation is, we need to find the remainder. Now the remainder of n equals to the sum minus the sum of n. Now this is using the integral test, so we need to check for if it's continuous, positive, and decreasing. If it is, then we can say that the remainder is greater than or equal to the integral from n plus 1 to infinity of f of x dx, but it's also less than the integral from n to infinity of f of x dx. In these two graphs of f of x and a to the n plus 1 and a to the n, we can see that a to the n plus 1 is always going to be less than a to the n. And so we can say that the remainder is somewhere between these two values. For an example problem, let's do 11.3, number 36. Number 36 says, how many terms of the series would you need to add to find its sum to within 0.01? Now, to use the remainder, we need to check that it's continuous, positive, and decreasing to use the integral. Now, using the formula for finding the sum of a series, we get that the remainder is less than or equal to the integral of the function from n to infinity, and we set this equal to 0.01 or 1 over 100. Solving for this, we get negative 1 over ln of x from infinity to n equals to 1 over 100. We get 1 over ln of n equals to 1 over 100, which also equals to ln of n equals to 100. So n would equal to e to the 100th. The second part of estimating a sum of a series is that we can use the bounds of the remainder to find a better approximation of the sum. So we can add s of n, adding the upper bound of the remainder and the lower bound of the remainder to get a better approximation. Let's do a practice problem. Using all we've been given in this section, let's solve this to see whether it's convergent or divergent. Now first we have to check if it's positive, decreasing, and continuous, which it is. Now, that means we can use the integral. This integral equals to the limit as t approaches infinity of negative 1 over x for t and 1. Solving this, we can get the limit of t as t approaches infinity of negative 1 over t plus 1. And this equals to 1. Because this converges, the series converges by the integral test. That's part 1. Let's find the accuracy to within 0.01. Put r of n is less than or equal to the integral from n to infinity of 1 over x squared dx, and set this equal to 1 over 100. 1 over x equals to 1 over 100. Because we are trying to find when the remainder is less than this, then x has to be less than 100. So x would be equal to 1 over 1. To find a better approximation of s of 10, we can say s is less than or equal to s of 10 plus 1 over 10 and is greater than or equal to s of 10 plus 1 over 11. S is between 1.64067 and 1.64977. So that's a better approximation of the sum. Common mistakes for 11.3 include messing up the integral in the integral test, so make sure to review your integral rules. And remembering that p greater than 1 converges, and just think of conceptual thinking. For a sum of series remainder, the remainder number has to be smaller, so always round up.